In this video, I'm going to show you how to use L'Hopital's rule to solve indeterminate limits. First, let's talk about what an indeterminate limit is. So a limit has indeterminate form if, when we try to evaluate it by direct substitution, we get a result of 0 over 0. And we call this indeterminate form because this result doesn't really tell us what the limit actually is. This might come out to 1, or it might come out to 0, or it might come out to infinity. We can't really tell. So we need to figure out some other way to compute the limit. And in this case of indeterminate form, we can use L'Hopital's rule. L'Hopital's rule tells us that if our limit has indeterminate form, it goes to 0 over 0, then we can use this rule here. We can say that the limit is equivalent to the limit of the ratio of the derivatives of the numerator and the denominator. So L'Hopital's rule just tells us that we can solve this kind of limit by differentiating the numerator and the denominator and then trying to take the limit again. So this formula is so important. It'll come up in the coming examples, and it'll also come out throughout calculus too. So we're going to box it and pay special attention to it. Let's do some examples now. For our first example, we'll consider the limit of tangent x over x as x approaches 0. So if we try to evaluate this limit by plugging in 0, we get tangent 0 over 0, and tangent 0 itself is just 0 over 0. So now we've got an indeterminate form of 0 over 0, which means we can apply L'Hopital's rule. So L'Hopital's rule tells us that we can take the initial limit, tan x over x, and construct an equivalent limit by differentiating the top and the bottom. So we'll put the derivative of tan x over the derivative of x. Okay, so now we'll go ahead and differentiate. So the derivative of tangent x, that's just secant squared x, and the derivative of x is just 1. So this limit is just the limit of secant squared x. And when we plug in 0 here, secant squared 0, that's just equivalent to 1 over cos squared 0, and 1 over cos squared 0, well, cos squared 0 is just 1, so that's just 1 over 1, so our limit comes out to 1 here. Great, so that's how we use L'Hopital's rule to solve that limit. Before we do the next example, I'm going to amend something that I said about indeterminate form and L'Hopital's rule. So indeterminate form, we saw on the very first slide that a limit has indeterminate form if, when we try to do direct substitution on it, it goes to 0 over 0. And the thing that I'm going to change here is that I'm going to also say that a limit has indeterminate form if it goes to 0, 0, or plus or minus infinity over infinity. So 0 over 0 is one case in which we can use L'Hopital's rule, and plus or minus infinity over infinity is another case in which we can use L'Hopital's rule. The next example is going to refer to this case, infinity over infinity in particular. But the process is still the same. We just take the derivatives of the numerator and the denominator and try to compute the limit again. Here's another example of applying L'Hopital's rule. So we're going to try to solve this limit here. And if we go ahead and plug in x is infinity, then we get infinity on top over 1 minus infinity on the bottom. So that's just infinity over negative infinity. So we've got an indeterminate form, which tells us that we're allowed to use L'Hopital's rule. So we'll compute the limit of root x over 1 minus natural log x by constructing an equivalent limit of the derivative of root x divided by the derivative of 1 minus natural log x. Okay, so let's go ahead and compute those derivatives. So that becomes limit as x goes to infinity. The derivative of root x is just 1 over 2 root x, and the derivative of 1 minus natural log x, 1 goes away because it's just a constant, and we've just got negative derivative of natural log, which is 1 over x. So we've got to pretty up this expression a little bit, and we can do this by multiplying by x over x. That'll cancel out the x in the denominator, and then we've just got the limit as x goes to infinity of, we've still got a negative from the denominator, and then x over 2 root x. Okay, so now we can go ahead and simplify a bit. That's the limit as x goes to infinity of negative a half root x. And we can go ahead and plug in infinity, and we get that's just negative infinity. So that's the value of our limit. Our limit goes to negative infinity. One caution when working with L'Hopital's rule is that if the limit does not have indeterminate form, then we cannot use L'Hopital's rule. And to highlight why this is the case, let's consider the limit as x goes to 0 of 1 over e to the x. So if we try to plug in 0 here, we just get 1 over e to the 0, and e to the 0 is just 1, so we've got 1 over 1, which comes out to 1. So this is actually the value of our limit. It's not indeterminate. We know exactly what it comes out to. It comes out to 1. But if we try to apply L'Hopital's rule, and keep in mind that this is invalid because the limit is not indeterminate. But if we were to try to apply L'Hopital's rule, we'd get limit as x goes to 0, 1 over e to the x equals limit as x to 0, derivative of 1 over derivative of e to the x. And derivative of 1 is just 0, derivative of e to x is just e to the x. So we could plug in 0, and we'd get 0 over e to the 0, which is 0 over 1, which is 0. But that's definitely not right, because we already evaluated our limit and we saw it came out to 1. So this is just an example that illustrates the caution that if a limit does not have indeterminate form, then we cannot use L'Hopital's rule, because L'Hopital's rule might actually mess up our limit and give us the wrong solution. Overall though, L'Hopital's rule is an extremely powerful tool for computing limits, and in the future we'll also see how to apply it when information is given in the form of a table rather than an actual expression.